Okay, so today we're going to go through the Chem 113 exam 3 practice exam. And one thing I'd really like to emphasize as you go through these questions is you really need to have a solid understanding of the mechanisms behind each of these reactions. A lot of these questions are testing details about the mechanism behind the aldol condensation, the Claisen reaction, etc. So let's take a look at question 1 as you'll begin to notice this idea. So the following aldol condensation yields a single product after dehydration. As we talked about in lecture, the aldol condensation refers to the dehydration product. The aldol reaction is typically used to refer to the initial addition product. So we're asked to predict the major and minor product from the following reaction. Draw a structure of the major and minor product from the first step of the following reaction. Explain why the major product is generated, and draw a structure or mechanism to justify your answer, and then draw a mechanism for each step of the aldol reaction for the major product. And then during the dehydration step, the minor product can be converted to the major product, and then we're asked to draw a mechanism for this reaction. Okay, so let's take a look here. So first and foremost, for any aldol condensation reaction, the first step when we treat this compound with base is we are going to deprotonate our acidic alpha position. Yeah, that's what we're doing. I'm drawing out the mechanism because at the end of the mechanism, we'll be able to answer each of these questions individually. So once we have our enolate can react with our electrophilic aldehyde to generate our aldol reaction product. This is going to be the major aldol product. In terms of our minor reaction pathway, we can try to deprotonate at our other alpha position, but this position is pretty hindered. So deprotonation gives this relatively hindered enolate. And from here, after attack onto our electrophilic aldehyde, we can generate the following minor product. Yes. This is for our initial aldol addition. The reason why this product is minor is this minor product is heavily strained. And because the aldol reaction is reversible, looking at this case, Is this strained product going to last very long? Would it be easy to isolate this strained product? Not really, not really. So because the aldol reaction is reversible, we'll primarily see this less hindered major product as our alkoxide ion in solution. So the explanation for why the major product is favored while the minor product is not observed is the major product is less strained. Well, for our minor product, due to strain, the retroaldol is favored. So if we have a choice between these two products, because this aldol reaction can equilibrate via retroaldol-aldol processes, this equilibrium will favor the major, less hindered product. Further, the deprotonation step also favors deprotonation at the less hindered position. Remember how in lecture we talked about how the aldol reaction for strained systems often favors the reactants? And how in many cases, if you have a strained beta hydroxyketone, it will undergo retroaldol? This builds on that idea. Does that explanation make sense to everyone? Okay, so we've answered B, C. We're almost done with D. So let's answer D and E next. Okay. So for our major product, if we have this beta hydroxyketone and we treat it with H3O plus and heat, we're going to protonate our oxygen and generate our beta hydroxyketone. And then we're going to protonate our beta hydroxyketone a second time to generate the activated leaving group, water. From here now, we can now drive this equilibrium to completion via deprotonation. And that in turn gives us our desired dehydration product. This is our major product. Does this aldol dehydration mechanism make sense to everyone? Yes, yes. I'm going to draw that right now. The minor aldol dehydration product would look like this. It's the opposite regioisomer, and this is not observed. To explain why this is not observed, let's take a look and let's sort of show what would happen even if we generated the minor beta hydroxyketone. Let's try to show why this aldol product is, whoops, there we go. There we go, perfect. So to answer the question why this minor dehydration product is not observed, let's show what happens under acidic conditions when you have this minor dehydration, when you have this minor aldol product. And let's show how this minor aldol product can be converted to the major dehydration product. Ah, yes, yes. You would also get the other alkene geometry, though generally you prefer to keep your alkyl groups away from the hindered alkyl groups already in your ring. But yes, you will also have one moment. So you do see a little bit of a mixture of the alkene geometries, but generally you generally want to avoid the steric clash between your ring and the alkyl group on your alkene. So this is typically very minor in terms of the other elimination product. Did that answer your question? You can mention it, but I'd prefer for the alkene that you draw the more stable, favorable alkene. Because under the reaction conditions, the alkene can isomerize and you see a preference for the more stable alkene. But you can mention both. Well, yes, in terms of IUPAC, in terms of IUPAC, you are correct in that this is a cis alkene, though generally the trans alkene is preferred. And the reason why the trans alkene is preferred is because we're separating our bulkiest substituents to minimize steric clash. This is just an odd quirk due to IUPAC and the definition of Z versus E and cis versus trans. Generally, when you form your alkene from dehydration, you want your alkene to be the least hindered alkene. You want to place your bulky substituents as far as possible from each other. Just the major and minor. The very minor other alkene geometry doesn't have to be mentioned. You can, but that's not the main point of this question. The main point of this question, as we've talked about and as we've seen, is that we want to clearly explain why one regioisomer is observed from this aldol reaction. That's why we get a major dehydration product and a minor dehydration product, and we don't see enough of the minor dehydration product. And that's because if we think about this aldol reaction, first, the major product, this initial aldol reaction, generates a less strained aldol product. And as a result, the retroaldol doesn't occur as readily for the major product. Further, the minor product would require deprotonation at the more hindered position and would require that after addition, they'd have to have this strained aldol product, which can readily undergo retroaldol to regenerate your starting material. And that's why the minor dehydration product is not observed. Does that make sense? Did that answer your question? Well, because the problem asks us to draw them out. And I'm drawing them out for completeness as well. Now, interestingly enough, even if you get the minor beta hydroxyketone, this minor beta hydroxyketone doesn't stick around for very long. if you treat this beta hydroxyketone with acid, what you will find is that rather than observing the desired aldol reaction, you'll see a significant amount of retroaldol processes. So in this case, under acidic conditions, we can protonate our carbonyl carbon. From here, then, we can kick out and lose our leaving group and reform our enol. And then from here, now that we've reformed our enol, we can then tautomerize this enol to generate the less hindered enol tautomer. And the real point behind this problem, the real point of this example, is just to show that even if we have the minor product, when we expose it to acidic conditions, we can in turn see conversion of our minor aldol product into the major product. Because now we have the following enol tautomer that can then react with our electrophilic aldehyde via an acid catalyzed aldol. And that in turn gives us the less hindered beta hydroxyketone, which from there we can protonate and then eliminate to get the desired product. So even if you had a little bit of the minor addition product, what you will see is that the minor aldol addition product can be converted into the major condensation product. Does everyone see how under acidic conditions, even if we got the minor beta hydroxyketone, it can be converted to the major product? Does this second mechanism make sense to everyone? So we're showing a retroaldol-aldol process. Yep, exactly. This is a key feature of the aldol condensation dehydration. You can funnel a mixture of beta hydroxyketones to the desired condensation product because you can promote a retroaldol and then an acid catalyzed aldol to generate the more stable beta hydroxyketone product. And this only works because the aldol product for the minor product is highly strained, and that makes the retroaldol occur quite readily. Does this problem make sense to everyone? The key thing I want you to take away from this example, strained products can undergo retroaldol, and it's important that you think about the aldol reaction as two steps: an addition that's under equilibrating conditions and under most cases, and then a second dehydration step. And we can see aldol reactions under acidic or basic conditions. Do the mechanisms make sense for this problem? And does our explanation make sense? Another case that we talked about is if an aldol reaction is reversible, then we can see retroaldol products in cases where you cannot dehydrate. So let's take a look at the next example. You can also see retroaldol if the dehydration step cannot occur, such as in cases where there's no available alpha proton. Did that answer your question? Okay, so let's look at these next questions. In this case, we're asked to propose a synthesis of the following molecule from compounds containing 4 carbons or less, and we cannot use an acyl halide in our synthesis. Okay, so we're going to break this bond, and we can form esters using the classic Fischer esterification. So we'll start from butanoic acid, and we'll just add butanol with catalytic HCl and heat. And that would give us our desired, this is N-propanol. So we get butyl propanoate. Propyl butanoate. So an easy way to prepare esters when you have a primary alcohol substituent is to use the Fischer esterification. Does this synthetic route make sense to everyone? Does this proposed synthesis make sense? Yeah, you can also, another route would be to go from the carboxylic acid make the carboxylate ion and then treat with the alkyl halide. That would also work. Yeah, so there are 2 main methods for this. Both are reasonable. Does this example make sense? Okay, let's look at the next example. In this case, we're asked to propose a synthesis of the following compound from the indicated starting material. This question's a little more tricky than it first looks. So you have the choice between going from the chloride or the alcohol. So if I were doing this, I'd break this bond and prepare this compound from this diol. So we know that in terms of reactivity, if we have a tertiary and a secondary alcohol, which of these alcohols is more reactive? The secondary, right? So if we treat this, for example, with triethylamine, and then we add acetic anhydride, that would give us our desired, not acetic anhydride in this case. We have to treat with the following anhydride to install this 3-carbon chain. And that would give us our desired acylation product. You can also use propanoyl chloride, both would work. And the key trick behind this problem is that only the secondary alcohol will react selectively because the secondary alcohol is less hindered. Now you may say, what about the other options? Can I do a Fischer esterification? Is it a reasonable idea to propose a Fischer esterification when you have secondary and tertiary alcohols floating around? Would this work? Would the Fischer esterification work? No. What instead you'll likely see is elimination, right? This tertiary alcohol is labile. So this is not desired. Let's look at the other option. What if you go through the carboxylate? What if you want to take this acyl chloride and you want to use the carboxylate? Well, when we have a secondary alkyl halide, you see some SN2 and you get some E2. So this route is less efficient. So generally, unless you are hard pressed to use a carboxylate, you generally want to avoid using a carboxylate when you have a secondary substrate. Because even though you'd get some of your desired product, you wouldn't get it as the sole product. You'd see a little bit of elimination, and that really cuts into your yield. So that's why this substrate was chosen, because it requires you to understand which alcohols are more reactive, and it requires you to understand limitations of the carboxylate and the Fischer esterification methods. Does this discussion make sense to everyone? Any questions on this example before we move on? If we don't have any other questions, let's look at this next example. In this case, we're asked to draw the mechanism for each step of the following reaction. So we're treating a carboxylic acid with phosphorus tribromide and bromine. So these are classic Hell-Vollard-Zielinski reaction conditions. So our first step is we have a strong electrophile, phosphorus tribromide. So our carboxylic acid will attack our electrophilic phosphorus atom. And that in turn generates an activated leaving group. Further, by forming this activated leaving group, we've activated our carbonyl carbon to further reaction with nucleophiles, even weak nucleophiles such as bromine. From here, this gives us a tetrahedral intermediate, and this is one of the few times where we're not going to be kicking out bromine. We can actually kick out our activated alcohol to give our acyl bromide product. From here, under acidic conditions, or under strong acidic conditions, we can tautomerize this ketone to the corresponding enol tautomer. And this enol tautomer can react with electrophiles such as bromine. That in turn gives us our alpha brominated acyl bromide. Which we can deprotonate in a cleanup step. From here, this alpha brominated acyl bromide can then be quenched and reacted with common nucleophiles such as dimethylamine. Dimethylamine will preferentially attack the carbonyl carbon, and that in turn gives us a tetrahedral intermediate. Triethylamine will pull off this acidic proton. And then from here, we can collapse this tetrahedral intermediate to get our desired amide product. So the only thing that's new in this mechanism is that rather than quenching with water, we're quenching our acyl bromide with an amine to give an isolable amide product. Does this mechanism make sense to everyone? Any questions on this mechanism for the modified Hell-Vollard-Zielinski reaction? Yes, you can use another equivalent of amine, but in cases where you have only one equivalent of your added amine, you usually need an external base like sodium acetate or triethylamine in order to deprotonate your product. Did that answer your question? Okay, let's keep going then. So in this case, we're asked to propose a synthesis of the following molecule from compounds containing 6 carbons or less. You can only use the following bases in our synthesis. You cannot use stronger bases. And then draw a mechanism for each step in your reaction sequence. So retrosynthetically, given that I have this carboxylic acid and I need to install multiple alkyl groups, I'm going to trace this carboxylic acid via functional group interconversion back to this malonic ester-like motif. From here, you can do it with, well, yeah, this should be 6 in the figure. Yeah. 5 carbons isn't unworkable, but it's a little more difficult. So we'll do 6 carbons, because that's what was specified in the main text. So from here, we can dialkylate this malonic ester. So we can trace this back to our malonic ester, which has 5 carbons and our 2 alkyl groups. In this case, we can alkylate the alpha position of our malonic ester using 2 alkyl halides. So in a forward sense, we can take our malonic ester and treat it with sodium methoxide, followed by our alkyl halide. And that would give our desired alkylated product. From here, treatment with another equivalent of methoxide and a second equivalent of alkyl halide gives our fully alkylated malonic ester product. And then we can treat with H3O plus and heat, and that gives us our desired product. So let's show the mechanism for each of these steps now. If we start with our malonic ester and we treat it with methoxide, we can deprotonate our alpha position and make an enolate. From here, this enolate can attack and displace leaving groups such as bromide via an SN2 reaction. But we're not done. If we treat this product with another equivalent of methoxide, we can make another enolate. From here, this enolate can react with other electrophiles, such as our alkyl halide, to generate our fully alkylated product. Is everyone following along so far? It does matter what base you use. You shouldn't use ethoxide in this process, or you'd get mixed transesterification products. And that would give quite a headache if you're trying to separate these products. Did that answer your question? Okay, so if we treat this compound with H3O plus, let's show the mechanism for hydrolysis and dehydration. So we're going to protonate our ester. Then water can attack our ester. From here, we can activate our leaving group via proton transfer. I'm just going to label these as R and R1 just to save some space. From here, we'll kick out our leaving group. And now we're just about ready for the key decarboxylation step. We just have to do one cleanup step where we deprotonate our carbonyl. Okay, and now for the key decarboxylation step, our beta keto group or beta carbonyl group pulls off a proton. We break our oxygen hydrogen bond and we break a carbon-carbon bond to generate the enol tautomer of our ester. From here, we can tautomerize this enol tautomer to the desired ester product. And the hydrolysis mechanism is exactly the same for how you can hydrolyze your ester further to the desired carboxylic acid. And that gives us our desired dialkylated product cleanly. Does this mechanism make sense to everyone? Any questions on this mechanism for alkylation and decarboxylation of malonic esters? Any questions on this mechanism before we move on? It's the same mechanism as the first hydrolysis. You protonate the ester, water attacks, you have a proton transfer, and then you kick out your leaving group. So this step, this set of steps here is just repeated. Yeah. Yep. In this case, you kick out an equivalent of methanol. Yep. Any other questions on this example? Okay, let's keep moving on then. So in this case, we're asked to predict the product of the following reaction and draw a mechanism for this reaction. So in this case, we're treating an ester with LDA and followed by another ester. So these are textbook conditions for a Claisen condensation. So LDA, lithium diisopropylamide, is a strong enough base to pull off our alpha proton and generate our enolate. From here, we can attack our electrophilic ester carbonyl. That in turn gives us our 1,2 addition product. From here, we can kick out our leaving group, which is, in this case, methoxide, because we have a methyl ester. And now, what's our most important step? So every step up to this point was an equilibrium, but in this final step, we're going to deprotonate our alpha position, and that in turn traps our Claisen product. So from here, our desired beta keto ester sits around as an enolate. And then when you quench it can be protonated to generate your desired beta ketoester product. Does this mechanism make sense? Yeah, for this problem, since there's no quench drawn, you just draw the enolate product. Any other questions on this example? Any other questions on this example? Okay, let's keep going then. Let's explain why the following reactant does not yield large amounts of product. So this explanation will usually require a mechanism. So let's draw out the mechanism and let's see if anyone has an idea. It doesn't have 2 alpha protons, yep. And why is that a problem? Well, let's see. If we deprotonate and form our enolate using LDA, lithium diisopropylamide, we generate our enolate and everything looks fine up until, it looks fine so far. Our enolate attacks the electrophilic carbonyl carbon, and that in turn gives us a tetrahedral intermediate. However, this is where problems begin, because no matter how hard we try, we can kick out methoxide, sure. But when we look at this beta ketoester product, this beta ketoester product lacks an available alpha proton. So we can't deprotonate. So instead, the equivalent of methoxide that we generated is just going to immediately attack our electrophilic ketone carbonyl. So we see retroclason. When I ask you to explain, you should ideally draw a structure or mechanism to justify your explanation, or at least the structure that showcases the point you're trying to make. No, you don't have to show the retroclason mechanism, but I can show it just for your reference. So we make a tetrahedral intermediate. And then we kick out our enolate as a leaving group. Did that answer your question? Okay, let's keep going then. So for this problem, we're asked to draw a mechanism for each step in the following reaction. So we have a beta ketoester and an enone. So this is textbook conditions for a Robinson annulation. So for our first step, methoxide is going to pull off the most acidic alpha proton, which is the alpha proton adjacent to our beta keto ester. From here, we generate an enolate that can react with the electrophilic beta position of our enone. That in turn gives us our conjugate addition product. And we're just going to protonate our enolate for now. Yeah, we're going to have to form another enolate. And I'm going to draw this structure a little bit suggestively to help us see this next step. Okay, so we now have our enolate protonated, and we're going to regenerate a new enolate that can react productively. So as we notice, if we reacted with our initial enolate, we would get a 4-membered ring. That's too strained to be allowed. So we're going to deprotonate to form an enolate that can condense to give a 6-membered ring product. From here, our enolate can attack the electrophilic carbonyl carbon, and that in turn gives us our condensation product. Many of these Robinson annulations that we discussed are textbook named reactions to prepare very important enones that have been used in a range of organic syntheses. So from here now, if we treat with toluene sulfonic acid and heat, we can dehydrate this enone. We can dehydrate our beta hydroxyketone to the corresponding enone. So toluene sulfonic acid will protonate our alcohol. We now have activated our alcohol as a leaving group. And then from here, we can just eliminate our alcohol to give our desired enone product. Does this make sense to everyone? Any questions on this problem before we move on? Any questions before we move on? Okay, so let's keep going then. In this case, we're asked to propose a synthesis of the following molecule from the indicated starting material. So how do we do it? So what reaction is useful for this transformation? What conditions would we need to convert this ketone into the carboxylic acid? And please only use conditions that we've talked about in this course. So what can we do? What reaction can be used to convert a ketone into a carboxylic acid? And this should be a methyl ketone, just for correction. What is a generic way to convert a methyl ketone into a carboxylic acid? What named reaction did we talk about? The haloform reaction, right? So if we treat with bromine and sodium hydroxide in excess, we can fully brominate the alpha position of our methyl ketone. And then from there, once we have this haloform leaving group, hydroxide can attack and we can displace our leaving group to give the corresponding carboxylic acid. So the haloform reaction is a useful method to convert methyl ketones into carboxylic acids. Does this make sense to everyone? Any questions on this example before we move on? Okay, so let's do some last bit of product prediction. So this covers the unique reactivity of amides and carboxylic acids. So if we have an amide and we treat it with lithium aluminum hydride, what product would we observe? What product would we observe? An amine, right? Rather than reducing the amide to the corresponding alcohol, amides are instead directly reduced to the corresponding amine. And we've covered this mechanism, I believe, in chapter 20. Let's look at this next case. So we treat a carboxylic acid with DCC and dimethylamine. What product will we observe? Not quite a Wolff-Kishner reduction. That involves hydrazine. So if we treat a carboxylic acid with DCC and dimethylamine, what product will we see? DCC is a classic reagent to prepare what? In either case, none of these reactions are quite a Wolff-Kishner reduction. That's indicated through use of hydrazine. So if we treat a carboxylic acid with DCC and an amine, what product would we get? An amide, exactly right. So we'd get the dimethylamine amide product. Any questions on these two examples? So with that, we've finished all of the practice exam questions. Any follow-up questions that I can address? As you can see, we got through the practice exam in a little bit over an hour. The exam will open up on Thursday and it'll be available for 3 days. And you'll see the module in Canvas. Can we finish the other mechanism, the reduction of the carboxylic acid? Sorry, I'm not sure what you're asking. Which mechanism was that the case? 5. Well, that's not reduction, that's hydrolysis. Sure, I can show that. We'll cover it down here and we'll just draw the general mechanism. So if you have a generic ester and you treat it with H3O+, first we're going to protonate the ester. From here, water will attack. We get a tetrahedral intermediate. Then there's a series of proton transfers. To activate our ester alcohol as a leaving group. From here, now that we have our activated leaving group, we can kick out our leaving group and get our carboxylic acid. And this mechanism is exactly the same as the first step. As a cleanup step, we'll deprotonate the carboxylic acid to generate the neutral form of our carboxylic acid. Does that mechanism make sense to everyone? Any questions on this example? Any other questions on this problem? Any other questions on this practice exam before we archive the recording? So with that, we'll archive today's recording.